Hello everyone. Today I am going to explain about on-chip clock generation and distribution. Okay, so if we observe in our digital circuits, there is more important for the clock signal. Okay, so that's why here on the chip also our integrated circuit also we have to use clock generating circuits. Okay, then how we can use this? How you can generate this clock and how we can distribute this clock we will see here. Okay, so that is what about the concept, that is on chip clock generation and distribution. In this one, so we are going to see about the clock generation and distribution. Okay, so here clock signals are the heartbeats of digital systems, hence the stability of clocking signals is highly important. I told that in digital systems, we are going to use or we are using this clock signal. Okay, so if you consider a flip-flop, if the circuit or IC consists of a flip-flop, okay, or a register, that is a memory element. Okay, so if it is a counter and all those things, in all those things, we are going to use our clock signal. Okay, so because of that, the clock signal is very important one in the digital circuits, and we can say that the clock signals are the heartbeats of digital systems. Okay, so hence the stability of clock signals is highly important. Ideally, the clock signals should have minimum rise and fall times, specified duty cycles, and zero skew. Okay, clock skew. So it is what here we have the requirement. Whenever you are generating a clock signal, we have to take care of that. Its raise time and fall time will be minimum, and at the same time, we have to maintain the specified duty cycles and clock skews. That is zero clock skew. Okay. So now here the next one is, in reality, clock signals have non-zero skews and noticeable rise and fall times. Duty cycles can also be varies. Okay, so here clock skews means what is clock skew means here is nothing but uh, if you apply a clock signal. Okay, so the time taken by this clock signal to reach the required place or required device is called as what clock skews. Okay, so if that clock skew is very less, automatically the delay will be less. Okay, that's why here we require a zeros clock skew, but in reality it is not taking place. We have the non-zero clock skew. In reality, clock signals have non-zero skews and noticeable rise and fall times. Duty cycles can also will be varies. Okay, in fact, as much as 10% of machine cycle time is expended to allow the realistic clock skews in large computer systems. Okay, so what is here? How much in large computer systems means here 10% of machine cycle time is expended to allow the realistic clock skews in large computer systems. But in VLSI, that problem will be reduced. The problem is no less serious in VLSI design systems. Okay, there will be a serious problem with clock skews, but here we will rectify that by considering different distribution and at the same time generation techniques. Okay, so a simple technique for on-chip generation of a primary clock signal would be using of a ring oscillator. Okay, so here you can have the circuit, basic circuit of a ring oscillator, that is simple on-chip clock generation circuit using the ring oscillator. So here all the inverters are connected back to back, that is sorry, inverters are connected one by one. The output of one inverter is given to the another like this. Okay, here we have two outputs, that is clock and clock bar, that is the inversion of clock signal. Okay, so here which circuit we are going to use? That is a simple technique for on-chip generation of primary clock signal would be to use a ring oscillator. Such a clock circuit has been used in low-end microprocessor chips only. Okay, so that is what here we have about the clock chip generation, sorry, clock generation on the chip. That is, it is a simple circuit, that is nothing but a ring oscillator, that is nothing but a ring oscillator. Okay, so this is about the ring oscillator, but we have some limitations for this ring oscillator that is used in low-end microprocessor chips. Okay, we can avoid that one by considering the different methods of generation. Okay, so we'll go with the next. So here the next one is what the crystal oscillator. It is a very stable frequency generator. Okay, so that's why we are going to use this crystal oscillator in VLSI circuit to generate the clock signal. Okay, so here the generated clock signal by using the ring oscillator can be quite process dependent, and it is unstable. The very important one is what? It is unstable clock. So if you apply unstable clock, it is a problem for us in not only in VLSI or in any circuits. Okay, so any clock dependent circuits. So here the generated clock signal using ring oscillator can be a quite dependent and unstable. Separate clock chips which use crystal oscillators have been used for high performance VLSI chip families. Okay, so this ring oscillator where we are using means it is in low end microprocessors we are going to use. But for high performance VLSI chip families, instead of using this ring oscillator, so we will go with the crystal oscillator. Okay, so the basic diagram of crystal oscillator as shown in here. Crystal diagram of a Pierce crystal oscillator circuit. So this is the crystal here we have, and C1 and C2, and here we have the resistance. Okay, so here we have, this is the diagram of crystal oscillator. Here we are going to use two inverters. One is the clock signal, and another inverter is used for the inverse of that clock signal. Okay, because we require both clock and in a clock bar. Okay, that's why here we are going to use two inverters. Okay, so that is what the problem with the ring oscillator. To avoid that problem, we are going to use the crystal oscillator on the chip for high performance VLSI circuits. Okay, now we have is here the Pierce crystal oscillator with good frequency stability has a near series resonant circuit in which the crystal sees a low load impedance across its terminals. Okay, so here we are going to generate our clock signal by using this crystal oscillator, and it consists of low impedance. Okay, so next series resonance exists in the crystal, but its internal series resistance largely determine the oscillator frequency. Okay, so what is it means? The clock signal frequency is depends on what? Mainly the internal series resistance. Okay, so here the internal series resistance of this crystal oscillator is very important because it determines the clock signal frequency. Okay, so in its equivalent circuit model, the crystal can be represented as a series of RLC circuit, series RLC circuit. Thus, the higher the series resistance, the lower the oscillation frequency. Okay, that's why here we have to keep maintaining this series resistance. It is equivalent circuit model. In its crystal oscillator equivalent circuit model, the crystal can be represented as a series RLC circuit. So to reduce that series or higher series resistance, what we have to do, we have to slow down, or we have to lower the oscillation frequency. Okay, so that is what here we have, right? Next one is the external load at the terminals of the crystal also has a considerable effect on the frequency and frequency stability. That is, whatever we are connecting at the external point or the external load for this crystal oscillator also determines the frequency of the clock signal, also affects the frequency of the clock signal. So that's what here the external load at the terminals of the crystal, that means here you are connecting two inverters like that, also has a considerable effect on the frequency and frequency stability. So this is about the crystal oscillator, and the previous one is ring oscillator. So those are the circuits that are used to develop a clock signal on the chips. Okay, so that is what on chip clock generation we have. Now next, the inverter across the crystal provides the necessary voltage differential, and the external inverter provides the amplification to drive the clock loads. Okay, suppose if you have here two inverters, here this external one will use to drive the inputs what we are going to connect for this. Okay, usually VLSI chips receive one or more primary clock signals from an external clock chip and in turn generates necessary derivatives for internal use. Usually in VLSI chip, we will receive one or more primary clock signals from an external clock chip and in turn generates necessary derivatives for its internal use. So in the on the VLSI chips, we are going to use one or more primary clock signal that are generated from the external chip, not on that chip. Okay, so but here we are going to generate this on chip clocks also. Okay, it is often necessary to use two non-overlapping clock signals. The logical product of such two clock signals should be 0 at all times. Suppose it is often to use two non-overlapping clock signals. Okay, so because of that, what happened here? The two clock signals should be 0 at all times. Okay, so this figure here, what I have represented, will generate two clock signals with two different that is nothing but non-overlapping signals, right? So if you observe here, I am applying suppose CK here. So it is inverted. It's inverted output. CK bar is given to this one and CK is given to this one, so that it will produce two clock signals, that is CK1 and CK2. Okay, so that's what here we have. So this circuit will generate CK1 and CK2 from the original clock signal. The original clock signal is CK, but if you consider the non-overlapping, that is overlapping signals means what? If they overlap, we don't get any signal there. We'll get only single signal. So that is single clock signal. But here this clock signal is divided into two parts. One is clock 1 and clock 2. Okay, this circuit is used as a used to generate different pair of non-overlapping clock signals. Okay, if overlap is done, so we'll get the 0 clock. Okay, at all the times. But here, if you consider this circuit will generate, say, a pair of non-overlapping clock signals from the clock CK. Okay, so this is about the circuit that will generate non-overlapping clock signals from the original clock. Right now, we'll have these are the generating points of the clock. That is, one is what ring oscillator, and another one is what we call crystal oscillator, and the next one is what? That circuit that will generate two non-overlapping clock signals from a single clock. Okay, so these are what we have the different generating techniques of on-chip clocks. Okay, now we'll go with how we can distribute them. Okay, so if you observe here, it is on-chip clock distribution. Okay, since clock signals are required almost uniformly over the chip area. Okay, so if you consider any integrated circuit, so on that chip, all the clock signals are uniformly distributed. Okay, it is desirable that all the clock signals are distributed with a uniform delay also. Okay, so all the clock signals will be distributed across the chip area uniformly. At the same time, all the clock signals must have uniform delay. Okay, they don't we can't arrange that non-uniform delay, because we'll get some problems, that is the clock skew problems and delay problems also we'll get. That's why while applying on-chip calculations or on-chip what we call on-chip supply of clock signal, so we have to go with two conditions. One is uniform delay and another one is all the clock signals that is distributed uniformly. Okay, then only we will avoid whatever the errors that are getting with the clock skew. Okay, so that is what here. So here for the distribution of this clock on the chip, I am going to use H tree. Okay, so what is that H tree and what is its structure? So if you observe here, this is the H tree structure. So what we are going to use to distribute this generated clock. Okay, so here we have seen three methods of generation. After that, the first point here is nothing but on chip clock distribution. In that one, we will see how we can distribute this clock throughout the surface of that IC. Okay, so here we are going to use H tree for the distribution of this clock. So if you observe this diagram, if you find at any point you will consider an H, you can observe an H shape. Okay, so first here it is clock generated. So that clock generated will generate the clock signal, required clock signal, and it will send like this and like this. So at this point, it is again distributed to here and here. So this is again distributed to this one. So if you observe this, all these structures, clock distribution structures on the chip is of the form of H. That's why it is called as H tree. Okay, so it will start here. Generally, tree means we can use this like this. Okay, from this one here we'll get again two like this. This is the tree representation. So here all these representations are in terms of a H. All these clock distributions are in terms of H symbol. Okay, that's why it is called as H tree. Okay, so this is what we have here. The tree means. So here also this shape is H. This shape is H here, and again in this one also we have H. That is H and H. Here also the big one is there. That is this line and this line. In between we have the one line, that is nothing but one H. So that's why it is called as H tree. Okay, H tree structure to distribute the generated clock on the chip. Okay, so in what is the disadvantage of this one? Okay, we will see here. In these structures, the distance from the center to all branch points are the same, and hence signal delay would be the same. However, the structure is difficult to implement in practice due to routing constraints and different fan out requirements. So if you observe this one, it looks like somewhat difficult because at one point we are going to generate this clock signal, and we are going to supply this clock signal throughout the chip area. Okay, that means there will be a problem will be created. Because of this, there is a equal delay concept we will get, but one point is nothing but the structure is difficult to implement in practice due to routing constraints. Routing is nothing but what? Interconnections, okay, between the modules. So that routing will be the problem if we use this H tree clock distribution circuit. Okay, so this is about the first case, that is on chip clock distribution. Okay, so now we will go with the next one here, the local decoders. So for this on chip clock distribution, so we are going to use another important one, that is local clock decoder. Okay, so local clock decoders means generally we have for the two inputs, it will give four outputs, that is 2:4 and 3:8 and 4:16 output. That is nothing but what? The decoder circuit. Okay, for the given two inputs, it will provide four outputs. That is nothing but input is 2, output is nothing but 2 power 2. That is 4. So generally the decoders will be indicated as 2:4 or 3:8 decoder like this. Okay, similarly here we are going to use these decoders to distribute the clock signals. So that's what here the name is, that is local clock decoders, because here we are going to distribute the clock okay, on the chip area. That's why these are called as what? Local clock decoders. Internally we are generating the different clocks from the given two inputs. Okay, so that's what we will see here. A more practical approach for clock signal distribution is to route main clock signals to the macro blocks and use local clock decoders to carefully balance these delays under different loading conditions. So what is this point here? Here a more practical approach is clock signal distribution is to route main clock signal to the macro blocks. Okay, suppose if I consider this one here, the main block. Here we are going to place at a particular point these macro blocks, and we'll apply to them, and those macro blocks will supply the signals to the local decoders, local clock decoders, so that they will divide the two signals into 4, and they will give the 4 clock signals at the output. So this is the importance of what we call local clock decoders, right? Okay, so it will balance the delays under the different loading conditions, right? The symbolic representation, what I told, if you give the two input signals, clock signals, the clock decoder will provide us 4 clock signals. Okay, so similarly here, the symbolic representation of this clock decoder is locally generated clocks decoder is this one. Okay, the local clock decoder circuit that takes the primary clock signals and generate 4 phase signals. So here these two are called as what? Primary clock signals, and they will generate here they will generate what? They will generate the different clock signals, that is 4 clock signals. That's why it is called as decoder. 2:4 decoder clock generator. Okay, so here we have simple waveforms and gate level implementation. Then how you can implement this decoder means by using this diagram. Okay, so next here we have is the different clock signals that are generated from this clock decoder. So here we have, if you observe this one here, that is CK23 is there. So the clock signal is started at this point, and this clock signal is started at this point, and clock 1 is started at this point, and clock 3 is started at this point. There is no much overlapping, or there is no overlapping of all the clock signals that are generated by using the local clock decoders. So here we are giving the two input actual clock signals, and they are performing that, they are giving that 4 clock signals that are not overlapping. That is very important here. Both 4 clock signals are not overlapping. So you can observe in this diagram, and this is the circuit used to generate those clock signals. Okay, if you observe at any point, both any two of clock signals generated cannot overlap. So that is the importance of these local clock decoders. Okay, they will distribute the clock signals on the chip. Okay, so this is another distribution point. Next, the reduction of clock skews which are caused by the difference in clock arrival times. So what is clock skew means? The difference in clock arrival times and changes in clock waveforms due to the variation in load conditions. It is a major concern in high-speed VLSI design. Okay, these local clock decoders will be used in our VLSI, but reduction of clock skews causes the differences in clock arrival. So if there is uniform delay in the clock distribution, it is enough. It is okay. But if you consider non-uniformity or the reduction of clock skews, which causes the clock arrival time, changing of clock arrival time. Okay, this causes the major disadvantage in VLSI circuits. Okay, or high-speed VLSI design. So this is about how you can distribute by using, one is what HT distribution, and another one is local clock decoder distribution. Okay, so now here we have how we can see another example here, how it will be distributed. Regardless of the exact geometry of the clock distribution network, the clock signal must be buffered in multiple stages. Okay, so here we have exact geometry. So if you consider here in this one also, it gives the exact geometry. That means it is taking 2 inputs and it is giving 4 clocks. Okay, so if you consider that regardless of the exact geometry of the clock distribution network, the clock signals must be buffered in multiple stages. Okay, so you can observe here, I will explain, to handle the high fan out loads. So here fan out means what? Okay, so the number of devices that can be driven by the output of a gate, okay, is called as what? Is called as the fan out. Fan out means here, suppose this is the output of this inverter. So how much capability it has to drive the output connected devices. Okay, so the output of this inverter is driving another 3 inverters. The output of each one driving another 3 here. So this output has a capability of driving these inverters. Okay, that is 3 inverters. These 3 inverters can drive 9 inverters, each one of 3. Okay, that's why here Regardless of the exact geometry of the clock distribution network, the clock signals must be buffered in multiple stages like this, as shown in figure, to handle the high fan-out loads. If you observe here, three-level buffered clock distribution network. This is first level, second level, and third level. So in the first level means what we have here. So one inverter, the clock source will generate the signal and it is given to the inverter. The same signal is applied to this inverter, and this inverter, so that it will give what? The inverted, here we will get the inverted one. So here we will get the CK bar, the inverted one. Here you will get, here you are getting CK bar, because the output is of this inverter is what? CK bar, because input is CK. So if it is given that CK bar, that CK bar is applied here, and it is CK bar, and it is also CK bar, because all the three are connected to the this CK bar, or the output of the first inverter. So after this one, CK bar means you will get CK here. So that is applied to again 3 and again 3. This is nothing but the distribution of the clock. Okay, so 3-level buffered clock distribution network, this one. Okay, so this is about the distribution network, another distribution network. Okay, so if you observe this one here, this output is given to this output is given to this output is given to this. Again, this is driving another 3, this is driving another 3, this is driving another 3. From this diagram, we can say that we can improve the fan out, okay, number of fan out loads. Okay, so that is what here. The next one is in the configuration shown in figure B, used in Digital Equipment Corporation alpha chip designs. The interconnect wires are cross connected with the vertical metal strips like this, metal 1 and metal 2. They are cross connected metal strips in a mesh pattern in order to keep the clock signals in phase. Okay, in order to keep the clock signals in phase. So what we are going to use, this type of structure we are going to use, that is used in what? Digital Equipment Corporation. Okay, alpha chip designs. Understood? So this is what about the clock distribution network used in DEC alpha microprocessor chips. Okay, now so far we have seen that needs for having equal interconnect length and extensive buffering in order to distribute clock signals with minimal skews and healthy signal waveforms. Okay, so we have considered here, so far we have seen the needs for having equal interconnect lengths and extensive buffering in order to distribute the clock signals with minimal clock skews. Okay, have equal interconnect length. That's why I told that all the clock signals on the chip can be uniformly distributed, so that you will get the uniform delay. Similarly, here this point indicates the same thing. So far we have seen that needs for having equal interconnect lengths and extensive buffering in order to distribute the clock signal with the minimal skew. Okay, so that is one here. In practice, designer must spend a significant time and effort to turn the transistor size in buffers and also the width of the interconnects. Okay, so widening of the interconnecting wires decreases the series resistance, but at the same time it will increases the parasitic resistance. Okay, so these are about on-chip generation and clock distribution. Okay, so now we have another small point here. The following points should always be considered carefully in digital system design, but especially for successful high-speed VLSI designs. So these are the points we have to remember while designing the clock generator. Okay, ideal duty cycle of a clock signal is 50%, and the clock signal can travel further a chain of inverting buffers with ideal duty cycle. So ideal duty cycle of a clock signal is 50%. Okay, right. The duty cycle of a clock signal can be improved, made closer to the 50% by using what? Feedback based on the voltage average. Okay, so by taking the feedback connections, we can improve our duty cycle of the clock to the 50%. Okay, so to prevent reflection in the interconnection network, the rise and fall times of the clock signal should not be reduced excessively. Okay, so next one is the load capacitance should be reduced as much as possible by reducing the fan out the interconnection lengths and gate capacitance. Okay, so the load capacitance should be reduced as much as possible by taking care of these 3 points, by reducing the fan out, the interconnection lengths, and gate capacitances. Another one is what the characteristics impedance of a clock distribution line should be reduced by using what properly increased width and height ratios. Okay, so the ratio of the line width to the vertical separation distance of the line from the substrate. The ratio of the line width to the vertical separation distance of the line from the substrate. That is the channel height, or we can also call as length and width of the channel ratio. Okay, the characteristics impedance of the clock distribution line should be reduced by considering the proper width and length, or width and height. Okay, so next one is the inductive loads can be used to partially cancel the effects of parasitic capacitance of a clock receiver. Okay, we can also use the inductive loads to avoid this clock skew. Okay, so next one is adequate separation should be maintained between high speed clock lines order to prevent crosstalk. Okay, adequate separation should be maintained between high speed clock lines in order to prevent crosstalk. So what is crosstalk means? If you are talking in your mobile, suddenly the call will be goes to another person. Okay, so that type of connection we are getting here is called as what? Crosstalk. Okay, to avoid that one, we have to use all these techniques. Also, placing a power or ground rail between the two high speed lines can be effective measure. Okay, so here these are what the different rules we have to follow while designing our clock generators and distributions. Okay, so this is about the clock generation and distribution, or we can also say that on-chip clock generation and distribution. Okay, thank you for watching. Subscribe our channel.